So in the last video, we talked a little bit about geometry shaders and how to modify the actual triangles of an object. But one thing that showed was you can't see the triangles behind here. And that has to do with culling. By default, if you don't enable culling of a specific mode, it will always cull the back face of the object. Culling, ZWriting, blending, everything that happens that way are all special shaderlab keywords. These happen before the HLSL program tag. So if we move that here and we go cull, and we just write off, we save that, what you can see is now we're seeing the triangles behind the object. We're actually seeing both sides here. So while that is good, there is also front, and we can call only the front face. So now we're seeing inside the object, and if I switch to the scene view, what you'll see is that it's like we're looking inside of it. And if I actually go inside the object, you can see everything on the inside, but you can't see the front faces of the mesh. You'll notice they're also all black. That's because of the lighting that we're figuring out. Since these faces are internal, the dot product of them with the light is going to end up being negative. So they're all multiplied by 0, so they all appear black. But we can also have cull set to back face, and that's the same as not having cull set at all. So to continue this demonstration, I'm going to set cull to off, and that way we have our faces here. So now there is a way in HLSL to check if something is the front face or not. So we can, in our fragment shader here, we're going to take in the geometry to fragment, as well as we're going to take in a bool, and this will be called face, and this semantics for this will be SV is front face. Now we can just quickly comment this out. We can go. So with that, we can tell it to return face half 4 1 0 0 1 or half 4 0 0 1 1. Now if we save that, we now have the front faces being red and the back faces being blue. So that's a way, if for some reason you want to render the inside faces differently than the outside face, you can use this semantic here, is front face, to change what you'll see. You could, in theory, sample different textures. However, doing that, you're going to run into a lot of dynamic branching. So there are ups and downs to it, but there is a way to figure out if it's a front face or a back face. I'm going to get rid of this here. I was just showing that you can look at whether it's front or back, but we're not actually going to use that. So just save that quick. So that was culling. We're also going to look at blending. Blending is how you determine the alpha of something. So there are a few different blend modes. So if we type blend and we do source alpha 1 minus source alpha, this is the default alpha based blending that's used for Unity. Now things are getting a little bit funky here. The reason why it looks a little weird is because the color we're getting, we're not clamping the alpha. So if we want to do that, what we're going to do is we're going to, instead of having this be here, we're going to do color times equals. We're going to put that there. And we're going to say color.a equals 0.5. The reason why it was looking weird was because the alpha was actually overlapping, and alphas start getting a little bit strange when they go past 1. So now we've set the alpha to be 0.5 for the whole thing. I could also change this to be, let's say here, let's get a half of an alpha. And while ideally you would not do this in a second texture sample, I'm just showing a way to do it. Since this is a black and white texture, I'm just going to pull the R channel. Instead, we can set this to be alpha. Now, it's darker or lighter depending on the texture, depending on what it sampled from the different points in the texture. It looks a little strange up here. That's because this is still actually ZWriting. So with transparent objects, you typically don't want them to ZWrite. ZWriting writes to the depth buffer, and it tells something whether or not it's in front of something else. So with alpha, you typically don't want to ZWrite because you want to work back to front. It basically, the camera starts rendering at the furthest point on the far clip plane and goes forward, and for each pixel it intersects, or each mesh it intersects that has alpha to it, it adds that alpha value to the transparency. Once it gets close enough that the value is 1, it just stays still. With opaque rendering, you use forward to back. So it goes out and it finds where the furthest object is from the camera. And then it says, okay, this is the furthest I can see because this object is opaque. I can't see anything behind it, and ignores drawing anything behind it. Forward rendering is cheaper than backward rendering. So typically you want to have mostly opaques, but if I don't have ZWriting set in this shader, by default the object is ZWriting. So even though we're saying it's transparent, it's actually writing to the depth buffer saying, oh, there's a pixel here, don't render what's behind it. Now if I go in here and I go ZWrite, and I change this to off, then I save that. Now you can see we don't have that issue where it was appearing in front of the skybox. Now it looks like it's not actually appearing at all, and that's because where the skybox is here, it's writing a depth value, the maximum depth value. It's as far away as possible. So when it does the backwards to forward rendering, it is saying this is infinity distance away. So it just never bothers writing the pixel. It's a cheap way of getting rid of it. So that's why if you have transparent objects and you're looking at them through the skybox, oftentimes they'll disappear. And that's because of how the depth buffer is working and how it's trying to figure out the transparent rendering, since transparent always happens after opaque. So that's one way of doing this. However, there are a lot of other modes beyond source alpha and 1 minus source alpha. We can do source alpha and 1. This is pre-multiplied alpha. And it's hard to see here, but if I switch ZWriting back on, despite the fact that we wouldn't have this typically in a shader, you can see just a little bit better here. This is pre-multiplied alpha. If I do 1, 1, now we have additive blending. So let me go down here and set this back to 0.5. Oops. So now with additive blending, what's happening is at each point where there are 2 pixels, rather than transparency adding up until it equals 1, it can overshoot. And what it does is it adds the colors of each of them to each other multiplied by their transparency value. So it creates it so that way when objects are overlapping, you get additive coloring and you get really bright HDR effects. If I duplicate this sphere a bunch of times, you can see it's getting brighter, and that's because it's blending with each of them and they're being added together. If I go back and change this back to source alpha and 1 minus source alpha, rather than getting brighter because the colors are adding, it just becomes opaque because the transparencies are adding. So there's lots of different blend modes. I just showed the basic standard alpha blend, additive blending, and pre-multiply blending. But there are lots of different ones. You could also see there was source color, 1 minus source color. There's dist color. There's a whole bunch of different blending modes. Generally, for most stuff, you're going to want to use source alpha 1 minus source alpha because this is standard blending. So those are the basics of blend modes. You'll probably just want to use source alpha 1 minus source alpha. That's really the most common one. That's standard transparent blending. But what I'm going to do is I'm going to comment this out. By default, if there's nothing, it treats it as an opaque object. And what I'm going to do is I'm going to turn ZWriting back on. So now if we go back here, everything's opaque. Even though we set the alpha down here, if there's no blending on, it treats the object as being opaque. Next thing we're going to look at is ZTesting. So by default, ZTest is L equal. And L equal will look the exact same. But if I quickly add in a cube, and I just put it here, let's say right there, it's blocking the geometry. If instead of being ZTest L equal, we say ZTest always, now even though this cube is actually closer to the camera than these points, we're telling the camera to draw it over top. So even if I move the sphere down below the world, it's actually going to end up being drawn no matter what. The sphere itself can be far below anything, but it'll always be drawn. If I change this back to L equal and save it, now the sphere disappears until I move it back above. Now, instead of doing L equal, we can do G equal. And instead, this is only going to render the mesh where it intersects or where it is behind something. So this is a way of making it so we can only see objects through something else. So if I move this sphere out of the cube, it's not going to work. But now that it's inside of it, you can see it. So this is a way of making it so you can only see it when the objects are intersecting with each other. You'll also notice that since I have it as L equal, you can also actually see, or sorry, G equal, you can actually see the back faces in front of the front faces. So when you're working with different keywords for shaderlab, you have to make sure you are aware of what you're doing, because as you mess with these things, whether or not you have the back face active or the front face active, you will get different effects. There are a lot of different ways to combine them together, but these are the 4 basic keywords. You could, in theory, also set this to never, and that just means the mesh will never be drawn. Why you would want to do that, I'm not sure. These cannot be changed on the fly, like at runtime. These are compiled with the pass, so these stay the same throughout the each instance of the material. You could make another instance of a material and tell it to set this individually and have it compile based off of a keyword, but by default, these are static. They don't change at runtime. So play around with this, find out what works best for you. That's the basics of the shaderlab keywords. Next video, we're going to go into HLSL keywords.